So I added this special little extra bit to the slide to download the 800 megabyte of prerequisites. Because one thing about machine learning is that a lot of it's being done right now on Linux, and a lot of it involves a fair amount of stuff to install. So I'm hoping that most of the people here got the email beforehand about prerequisites and did the magic Docker command that pulls down the huge bundle that you need to do that. Just so I have a sense for where we are right now, if I could have a show of hands, people who have done the Docker command, raise your hand. Wow, this is a group that does their homework. That's fantastic. Okay, great. So no one needs to go to that link that I was putting together last night. We're ready to go. And if you want to look at your phone, actually, I don't mind. I understand phones are an important part of our lives these days. So just to start off, I'd say that the organization of the agenda of this session is going to be a little bit different than others because of some of the compute limits posed by looking at machine learning. This would be the kind of logical, straightforward way to organize it. Right? We have a nice long chat about like what machine learning is with some basic concepts, and then we go into that and we'll work out then some exercises that use those concepts step by step. But unfortunately, that wouldn't work because the only way we could do that is if we didn't have a very little bit of time to do the exercises relative to how long it takes to do something interesting with machine learning. So we'd be forced either to do a model that was like so simple it was a bit boring, or we just wouldn't have time to do a model. So instead, what we're going to do to reflect this reality of only so much time to work with and only the computers that we have in front of us to work with is a slightly different structure. Instead, what I like to do is dive right into a demo, which is going to be more or less following instructions without me explaining them too much, because what we want to do is we want to get the computers working as soon as we can. And I didn't want to do something with canned information where everyone was doing exactly the same thing, because I think one of the important points to take away about machine learning is that you can build your own models with your own data right now. You don't need to be a mathematician to do that. There's enough good tools available to do that. So I thought it was very important that we all actually gather our own personal data. Everyone's going to have different data on their computer. And then everyone here is going to train their own model with that data. So we need to start the training process immediately, because it's going to take at least 15 minutes of solid compute on an older machine and probably 5 minutes of solid compute on a really modern machine. So get your CPU engine started, and we will get on with that bit right now. So a lot of what we're doing here, we're going to be doing in the terminal. There's not going to be much Xcode at all, maybe none. There's a little bit of Swift, but this emphasis is on machine learning, not the iOS part. So first step, is let's go to your desktop, and it should look something like, well, you're not going to have those. Oh, my desktop is missing. Exciting. Okay. Never fear. Here it is. There's a version of the desktop. So you should have this folder, prerequisites, and one of the assets that you downloaded should be this tarball, Inception 2015-1205.tgz. And the first thing to do is, let's say this is the root of the repository for the work that we're going to be doing. Hang on, let me do the 2-monitor shuffle. Let's go into the machine learning part, and we're going to be doing all of our work out of this directory called tutorial package in the command line. We're not broken into the start-or-finish structure because everyone's going to have a unique finish, so I can't give you a canned finish. And open the assets folder. And then there's a folder in there called large-binary-assets, which you may need to create if it's not there, but it should be there. And what you want to do is just drag and drop Inception into large binary assets to make sure that's in place. All right, so there it is. That's step one. And if you've done that, and if you also did the docker pull command, then we're good to go in terms of other assets that need to be ready. Can everyone read that? Is that clear? Raise your hand if you can read it. Great, fantastic. So if you're in the tutorial package, you should see something like this. And now we're just going to go through a few instructions without explaining them too much to get the process started before we begin a discussion of what exactly it is that we've just started going. So first, let's run step 0 dash prepare working directory. You should see something like this. And now in the tutorial package, you should see a subdirectory tf_files. This is where all the live data that we build up and the training data that's built up through the training process is going to be placed. TF stands for TensorFlow files. And you might need to create this directory structure if it doesn't already exist. Let's have a look at what that is. So we want to make sure there's a directory called images, which there is on mine, so that app's not doing anything. You want to make sure there's a directory called images smiling. Sure. Images frowning. Images raw. Frowning. Images raw. Smiling. And there should also be a directory called videos, which may already be there. So now, everyone should see a directory structure that looks a bit like this. Images, frowning, smiling. Images, raw, frowning. Images, raw, smiling. And videos. So let's take a minute for everyone to get there. Could people when you reach that point with your directory structure, could you raise your hand? All right, good. We're almost halfway there, so let's wait a little bit longer. So just to give a little description of what we're doing right now, a very typical part of anything you do with training any kind of machine learning model is, to be honest, a lot of somewhat tedious pre-processing of data before it's ready to go into the model. And we're going to be doing a little bit of that as well. As I'll say a little bit about more in the discussion, I'm just giving a preview of it here while we wait for people to add these directories. Interesting models tend to be ones that use a lot of data. The sensor that we have on the device that makes it easiest to gather a lot of data right now is the camera that's built into all of your laptops. So we're going to be gathering video information and then using that to create data that we pre-process before we build the model. Let's have one more go at it. If you have this directory structure and ready to go, then raise your hand. Or raise your hand if you're not going to follow along with the details so you don't have it and you're irrelevant to the discussion. All right, one more time. Hands up, just to see where we are on that point. OK, looking good. All right, let's go to the next step. All right, here comes the fun part, everybody. So what we're going to do is everyone here is going to build a machine learning model that knows about them. It's for classifying their facial expressions. In particular, what we're going to do is we're going to build a classifier that can tell the difference between you smiling and you frowning. And to make it a bit easier, let's not do like little smiles like and little frowns like Let's do big smiles like, hey! I think like Fonzie smiles like, hey, this is me doing an easily recognizable smile, yeah? And this is me very sad if I realize my presentation assets aren't ready. Like, this is my frown face. We're going to gather this right now by using Photo Booth. So launch the Photo Booth app that's built into your Mac. There I am. OK, we're now gathering data. First, before I start smiling, I don't want to feel like I'm alone with this. So can everybody just smile right now, just so we're sure we know how to do this part of it? Are you smiling, sir? Smile. Are you smiling, Greg? Are you smiling, Ray? Do I see any non-smilers? All right, good. All right, I feel like it's a party now because we're all smiling. OK, so here we go. Machine learning. I'm about to gather 10 seconds of video. So in order to use Photo Booth to take video, which probably we don't do all day, go down to the segmented control in the bottom, go to the rightmost lozenge, tap it there. Here comes my smiling face. And here comes me capturing data. Oh my God, I'm so happy for 10 seconds. There we go. OK. That's 10 seconds of me smiling, gentlemen. And notice it doesn't need to be the same smile. The whole point of this is to be able to detect a variety of smiles. So I presented my best smile variety. All right, there we are. Awesome. OK. Now you're going to see my sad face. So let me now record. Let me finish that so it displays the record controls again. 10 seconds of me being sad. All right, it's not how I actually feel, if you thought that. So now, everyone else, I need you all to do this. You all look very amused by my smiles, but it's time for me to see your smiles. So if your photo booth ready, everybody capture 10 seconds of your best smile. Bigger smiles, people. Make it easy for the computer. Who's got, raise your hand when you have 10 seconds of video of yourself smiling in Photo Booth. Awesome. OK, now 10 seconds of yourself frowning. So everyone, put on your sad face. Let's see 10 seconds of yourself frowning. Where's those frowny faces? You guys are so happy. You're better at smiling. I can't tell if you're focused or you're frowning. Greg, did I see you frown? OK, great. Thanks. You want to see my other? Yeah, this is me training smiles at work. There's my boss training his smile. Here's me at home smiling. Me at home frowning. Anyway. OK, so next step. Go into the videos folder that we created. And with Photo Booth, I want you to drag your smile, the one you just did, into the videos folder. And now also I want you to drag your frown into the videos folder. OK, that's enough of that. So there's this is my smiling one. Now, and I need to rename this smiling.move, smiling.quicktime movie. And this one I'm going to rename frowning.move for the frowning QuickTime movie. And these names are important because the scripts that we're going to be running next expect those to be the names. And later on in the lab session, when we have a chance to build another classifier, similarly, the names are going to be important. So you might create a name, something like doing nothing.move or not there.move. So next step.
I can't see like casing or anything, and the Finder text is very small.
Oh, sorry. So should be case insensitive, everything we're doing here. But videos should be frowning.move and smiling. Oh my gosh, that's totally illegible. So I could try to mess with the display scale right now, but that also seems like a risk given the issues we had before. Good thinking. Thank you. Thank you for pointing that out. I wasn't aware of that issue. OK. All right, great. So we're just about good to go for the next step. So you want to be in the tutorial package directory, in the terminal. And now comes the science part. First, we're going to generate images from all of this. So for that, we're going to be doing this command, step 1, preprocess training data. Here we go. This is where we use a little bit of Swift, because there's a little Swift script I wrote that takes the QuickTime movie and generates a lot of images from every frame. And then we're reducing the resolution of the images using a command line tool called SIPS, S-I-P-S, which is built into your Macs. This shouldn't take too long, but it might take a couple minutes. And just so you see there's no magic, so now if you look in the Finder, you should see a structure like this, where smiling directory has images, frame 0, frame 1, frame 2, all a little bit different. Some of them very different when I like open or close my mouth. And there's also an images raw directory that really just has the same images but at a higher resolution. Hopefully that's not all how you're all feeling now. And just to show you there's no magic going on, we could look at the text of that shell script, but we can do that later. So next step, we want to make sure that everybody has installed Docker already. That was one of the prerequisites as well. Could everyone raise their hand if they have successfully run the pre-processing step to generate the image data? Awesome, great. And everyone, I assume, is already, if you've managed to install a Docker image from a SHA hash, I'm sure you've managed to install Docker. So let's just assume everyone's got Docker going. If you want to check that, next step here would be, you could say Docker version, just to make sure that you have a version of Docker that shows up. Anything that's that version or later, I presume, would work. That version's the safer one. Now let's make sure that you have that TensorFlow image installed. This is really just a check, because if we don't have it installed, it's certainly too late to download it. Step 2, load TensorFlow into Docker. Nothing to do. You have already loaded the needed image. Bravo. If everyone could raise their hand when they're past that. Great, awesome. OK, and now we start training the network, and then I will talk a little bit about what's going on. So step 3, train model within Docker. All right, so you should start seeing console output like that as we start building the neural network. Now, let's so if everyone could raise their hand when they're at that point. OK, seems like we're all getting there. I will. So again, that command is /step3 train model within docker.shell. If you run it from within the tutorial package directory, that will start the model learning process. And now let's talk a little bit about what that means and what we mean by machine learning. So what is machine learning? There's a lot of hype around it. And you can offer a lot of definitions based on like what people are talking about. But if you want to be kind of rigorous and simple, an accurate definition is just to say machine learning is any approach where you're defining an algorithm not based on analysis, not based on sitting down and scratching your head and thinking about what the function definition should look like, but defining an algorithm based on data. I mean, that's really what it is essentially. So if you take that expansive definition, then strictly speaking, machine learning is everywhere. It's not new. Predictive typing has already learned data about the words in the dictionary, about words that you typically use, your spam filtering. Face detection didn't work. The face detection algorithms that are in your phone that are used by your camera app, those aren't based on someone having done a priori analysis about what a face looks like. It was based on a database of faces like the one that we have at my work. OCR, recommender systems, all of these are machine learning systems. It's been around for a while. It's not especially new. Just to emphasize that point, that we're just talking about any function that's defined in terms of data. We could here imagine this as being the world's simplest machine learning model. I point this out to emphasize the point, and also because it's a good starting point for defining basic concepts in machine learning that we will use later to understand the model that we're building right now on your system. So this model is a model that predicts height. And it does it by me picking 3 people in this room and measuring their height. I'll measure Greg and Ray and you, sir. Right? So let's say those are the heights. That's what we'd call the training data. It's the data that we're using to train the model. This model is supposed to predict heights for everyone in the world, but we're only looking at these 3 people in order to start the training process. Now, what is a model? A model is just the algorithm that we're going to use. This is the world's simplest machine learning model, so my algorithm is just going to be, I'm going to take the average of everyone's height, right? And in that case, training the model is really just doing the computation that performs that average. Whoa, that's exciting. I could unplug it and plug it in again. Oh, it's power. Well, I can keep talking through this because it's a basic point while the gentleman helps with the screen. And now we'd say if we had this model, which was just a function that returned whatever we computed that average to be, then the business of just calling that function and returning that constant value that we've pre-calculated, that's what we call exercising the model. That's what we call inference. So we have the training data that you use, the definition of the model, the process of training the model, and then exercising the model. We could elaborate it, make it a slightly more complicated model. So let's say that instead of measuring 3 people, I measured 3 men and 3 women, and I took the average of the men and the average of the women, and then I computed an average for each, and then my function, instead of just always returning the same number, the function would take in, well, what's the sex of the person I'm trying to predict, a man or a woman, and then it would return either the constant I got for a man or the constant I got for a woman. So that's also a totally trivial, uninteresting, but genuinely sort of machine learning model. It's getting a little bit more elaborate now because my model is 2 averages, and my training data includes 6 people with 2 different categories, male and female, but it's still a model. You don't need to go very far beyond this level of simplicity until you're talking about the kinds of models that people actually use. So, let's say that instead of just checking if someone were a man or a woman, I measure your shoe size, your belt size, your weight. Let's just say I'm looking at your height, and I'm using that to predict what your weight is instead of just using an average. Then my training data, for instance, if I were using height, would be a set of pairs. Like this is the weight that I'm trying to predict, and then this is the height I already know. And I could imagine myself coming up with a function that had a shape a bit like this one, where, well, I haven't written it here, so that's a mistake. But that would have a shape which is basically, I have an offset number, which is like the weight everyone starts with, plus something times the height that I measured. So I've only got 2 parameters that I've worked out there, and that's what we call a linear regression. That's a big word for a small thing. A function is just a constant plus another constant times the input that you've got. So if I were going from height to weight that way, that would be a kind of univariate linear regression. That's another machine learning model. And exercising the model again, in that case, would just be the constant that I've learned plus the other constant times the height that's gone in. So, to recap what this means here, it's okay, I've got a table and you only need to see the right side of it. So, so we're good. So we're perfectly good. So to recap what we mean here, in all of these contexts, we have these basic concepts that appear. Training data, in the cases they say the mean height model would be the heights that I measured for 3 people. Model is the idea of taking an average. Training it is actually calculating that average. Number of model parameters is the number of numbers that I computed in the course of training the model. If it's the mean height model, then it's just one number. Whereas if I was looking at the linear regression, it's 2 numbers. It's the offset and the slope. And then we could also talk about what we might call the error, or is more often called the loss, which is just if I now make a prediction about that person in the back, about, say, Tammy, and she wasn't in the training data, there's going to be some deviation from what I predicted and what I actually get. That's the loss. Now, 2 other concepts that are relevant here. If I then wanted to sort of get a sense for how well this model was doing, I wouldn't look only at the people I trained it on. Right? I wouldn't go to the 3 people I used to calculate the mean and then look at the error with respect to them. If the point of this model is that it's supposed to predict for everyone, then I might only train on this small number of people, but I'm going to look at how well it performs over a larger group. So just like there's training data that you use to train the model, there's a larger set of data, larger number of people who you're sampling to check for the error that matters, and that's what you call your validation data or your validation set, sometimes called your test set. There's a sort of subtle distinction there. And this concept of overfitting, which we'll get to later on, is the concern that if I pick 3 people who are a bit unusual and I've trained on them, say I pick the 3 shortest people in the room and I train my model on them, well, I'm going to have a model that's really good just for that training group. And it's going to end up producing an error that's really bad for the larger group because the model is overfit on the small amount of data that I was using to begin with. So again, maybe you're thinking this is not new. Like I kind of get the idea of a linear regression. We knew about linear regressions back in the late 19th century. This gentleman here discovered the linear regression in the course of studying heritability on sweet pea flowers. So if this is so basic and old, like why do people talk about machine learning now? Why is it a sort of trendy topic? What gives? The answer is essentially that we have a lot more data than we used to, and we have a lot more compute power than we used to. And as a result, we can apply models that are decades old, or are a relatively small variation of models that are decades old, but we're starting to get qualitatively different behaviors out of those models, and that's what's interesting. So, we could make a little app here that did a linear regression where we measured 3 heights and calculated the function. Obviously, that's not what y'all showed up for, right? Like that doesn't sound very cool, even though it's technically machine learning. A lot of the interesting models now use a lot of data, which is why we're training it here, and they're based on neural networks. And neural networks are a great example of the kind of thing that has existed since the 50s, but is now different. So just to refresh what a neural network is, I like to think of neural networks the way I like to think of many processes in life itself, really, as nothing more than a kind of function. It's a system that takes some values in, does something, and then it spits other values out. There's input arguments, and then there's return values. So if we look at this very simple toy neural network, like the kind you might have drawn on a napkin in the 50s, you have 3 input nodes. You can loosely think of them as being a bit like a conceptualization of a neuron. And those are your 3 input arguments to this function f. And there's 2 output nodes. You can think of those as like neurons. Just like this function here returns a tuple that has 2 output arguments. And inside it's doing something, which I haven't written the code for. But if you want to think about what the process is, you can imagine there being other nodes that are only activated temporarily or transiently. And I could write in little numbers into those circles. If the input arguments were 1, 2, 3, we'd write 1, 2, 3 into the inputs. And then all the lines that go from input to hidden are the connections between the neurons. So every one of those lines would have a little weight. I could say 1 is a half, 1 is a third, 1 is a quarter. And that's determining how we calculate the values from those intermediate variables from the inputs. And then similarly, we have all these weights on all the connections that go from the middle layer to the output layer. And if I were actually going to write it, it wouldn't be quite this simple because we apply a sort of smoothing function to some of these results before we spit them out. But you could imagine it at a really basic level, one that didn't have certain nice points. That's not a great demonstration of it. Yeah, okay, we're back to the good half of the screen. But one could imagine the function that's applied even looking a bit something like that. You have like inputs that go in, they are multiplied against some magic parameters that our model just knows. The model parameters sort of L1 up to like L43. And then there's more, those express all of the weights for the first layer of links. And then to go from the middle layer to the out, you have another set of magic parameters, which are the weights for that second set of links. And it would be a little bit more complicated for a realistic network, but one thing you might notice just looking at this, if you've done a little bit of work with so much suspense, with core graphics or core animation, is that should look a little bit familiar. You might look in that and say, that looks a little bit like matrix multiplication. Right? Like when you see a definition of matrix multiplication, there's this grid of values that are the matrix, and you're multiplying it against one vector, and that gives you another vector. Why do I point this out? Well, the reason is that part of the reason we're able to get very good performance out of neural network machine learning models right now is that it's possible to express a lot of the computation that we want to do in terms that look a bit like matrix multiplication at points, look a lot like linear algebra, and are easy to parallelize, because these are the sort of computations that our GPUs are really good at doing now, because GPUs have been designed to support these sorts of computations from decades and decades of people wanting better and better video games, basically. So that's still a kind of boring-looking 1950s model where you have a total of, say, 20 trained parameters, 3 in, 2 out. You might think this doesn't produce interesting results. Fast forward to where we are now. This is a high-level diagram of a neural network model called the V3 version of Inception. This was introduced just last year, so this is very close to the cutting edge of the best that people come up with. And instead of having one intermediate layer, there are 48 layers total. Each of those layers is quite complex. They're not fully connected so that everything from here goes into here. There's optimization, so you're only taking little bits of information, so it's still tractable. And instead of having 20 trained parameters, fully training the Inception neural network takes quite a while, even on good hardware, because it has 20 million 32-bit float parameters to define all of the weights. And this legend in the left, I don't think it's quite legible, but we'll look at this later. There's a categorization for different kinds of operations that are happening in layers. Pooling layers that collect lots of information from an image and reduce it to something that's sort of summary. Fully connected layers that were like the last one that we looked at from the 1950s, where everything from here connects to there with different weights. And then layers that take what you have and turn it into something that looks like a classification. Now you may be wondering, what's this for? The Inception model is used for image classification, which is what we're doing. Now you may ask, well, how do we go from something like we saw before that had 3 inputs to something that goes from images to classification categories? Well, the thing is, like under the hood, it's all just ones and zeros, Johnny. It's all just like numbers. So if you take an image, you can say you have a 1,000 by 1,000 image. You can with 3 colors, you can stretch that out into a single vector that's 1,000 times 1,000 times 3 bytes, because you're just laying out all of the channels of information as one long vector. So instead of imagining that row with 3 inputs, you imagine a row now that's 1,000 times 1,000 times 3. So you're dealing with very large vectors, and that's the sort of representation that you can use. So models like Inception have produced startlingly better results than we used to get just in the last few years. Not just image classification, but other areas of machine learning as well. And this is being shown in benchmarks that people have been doing for years as part of research and contests. So this is the webpage for the ImageNet Large-Scale Visual Recognition Challenge. They do it every year. Best case, I think Inception had, I don't have my presenter notes here, but I think Inception had was correctly guessing the category of an image. So here's an example of the sort of data that you work with. You get lots of different cats, and a network is performing well if it's able to recognize that one of these images is a cat. And when you think about it, as programmers, this is kind of a hard problem. It could be a different background. Cat could be looking at you. Cat could be looking away. Very hard to think a priori how you'd write something that does this. So the Inception model, for instance, if you give it an image and then it gives you its best guess on categories that it falls into when it's trying to guess one of 1,000 predefined categories, if I remember, it is putting the correct answer in the top 5 category, in the top 5 of its prediction. I think it's like 92% of the time, but quite good, really. So that's very cool and science fiction-y. But just to pull this back down to the concepts that we introduced before, in our trivial, say, linear regression model, the training data was heights and weights of, say, 3 individuals or 6 individuals. For something like image classification, the training data that's used for that database, I believe, is 1 million images. It's a lot of data that's going into it. The model's not a linear regression with 2 parameters. It's 48-layer deep neural network. Training the model is not something, with a linear regression, it's something you could do analytically. You could write a formula that gives you the slope and the offset. But when you're dealing with a model that has this many parameters, you can't write a single formula that's going to spit out the result. There's an iterative process of multiple steps that your training system will go through in order to find better and better parameters. And that's what your computers are doing right now. They should be nearly done, all of them. And loss for the linear regression is how bad the prediction is. Loss for a classifier is rate of classification errors. How long do I smile, but then for a particular image, but then it told me that I frowned. And ideas like validation and overfit carry over as well. So if I were training Inception on those images, and then I give it other images of cats, and it's terrible for anything that I didn't train it on, then what's happened is I've overfit. And that becomes a bigger and bigger problem when you have a very complicated network like Inception. Because the more model parameters you have hiding in the network, the more things you're training, the easier it is for the network to just memorize effectively the training data you've given it, because it has all this storage. It has 20 million bytes of storage, so that's a lot of information. So for instance, I think that the company Baidu may have been, I think it was disqualified from the ImageNet Visual Challenge for 1 year, because when they looked at the logs, they realized that they were peeking into the validation data more often than they were allowed to with scripts. And so you can get amazing performance if you're just overfitting on the validation data. You're only supposed to be training on the training data and then having your performance judged on this broader set of images. So this issue of overfit is a real one and a subtlety. So what does Inception give you? It lets you do image classification. In fact, Apple has already released sample code in the last WWDC that implements Inception on iOS. It's a very involved, specific process, but this is me running the app that you could all get from Apple. I've taken a picture of a bottle of water when I was on a flight, and there it's telling me 77% chance that's a bottle of water. Interesting that it's showing 1% chance it's an oxygen mask. I think it has somehow figured out I'm on an airplane. And if you're on an airplane, sometimes people are taking pictures of oxygen masks. So you can see there's a sort of inference process that's not exactly the way we'd think about it, but that works pretty well if you know you're going to have to guess within a category of 1,000. Another way to summarize why people are excited, or why people talk about machine learning a lot, would be to say, look at this XKCD comic, where someone's asking a programmer if they can tell if there's a bird in the photo, and they say, yeah, that's a research project. It'll take 5 years. So this was punchline of a joke in 2014, but in 2016 we have Apple sample code, which could probably identify a bird quite accurately. So that's kind of cool. Within 2 years we've gone from punchline to something that you could just download and run on your phone. So these new results are part of the reason that people talk about machine learning, but also the quality of the results is different. How does a model like Inception, which is called a deep learning model, work? Partly they're called deep because they have a lot of layers. So if you just imagine stacking up the layers, you'd say that's a deep stack. But partly they're called deep learning models because the way they work seems to be based on the early layers detecting very basic primitive features, and then the intermediate layers using those primitive features to detect higher level features. So in a sense, they're discovering the intrinsic conceptual hierarchy. They're having a sort of deep insight, if you will, into what it is they're looking at. So for instance, you're just inputting data as raw pixels. You're not saying anything except there's a red at this position, there's a green at this position. But the first layers of these models tend to end up doing something that's a bit like edge detection. They're going from this simple idea of like yes or no, or bright or not at a spot, and then the middle layer is doing something like saying there's an edge here, there's an edge here. And then higher up you get identification of, well, there's a shape that's curved versus there's a shape that has sharp angles. And through that process of inference, eventually you get to these higher level sort of summaries of what's going on in the image that are useful enough that they can actually be used to do something like say, is that a cat or is that a water bottle? And that's kind of magical that these systems end up working in that way. This is a bit of a tangent, but I can't risk mentioning it. I can't avoid mentioning it because it's just so cool. But they're also doing something that's very strange. Like these are all examples of incorrect classifications produced by absolutely modern state-of-the-art neural networks. So that image on the top left there, it thinks that's a centipede. Most people wouldn't make that mistake. It thinks that thing in the bottom right is an electric guitar. It thinks that's a starfish. It's interesting to think about like what's going on in their heads that would cause these images to be misinterpreted in that way. Okay, now why this detour to explain why deep learning networks work this way, and why looking at neural networks in particular. The reason is because the Inception network is for instance, and other image recognition networks, are picking up these low-level features and, in a sense, thinking by finding these intermediate-level features, you get the possibility of something that's called transfer learning. And transfer learning basically means I built this network by training it to do as good a job as it can recognizing 1,000 random images. But now I want to use the same network to do something else. Instead of recognize the same 1,000 images, I want to be able to use it to recognize just two different kinds of images, an Alexis smiling versus an Alexis frowning. Those are totally different problems, like water bottle versus cat versus 998 other things. It's a very different problem from Alexis smiling versus Alexis frowning. But because the thing that we trained to recognize the 1,000 things worked, in a sense, by learning fundamental truths about vision, this is an edge, this is a corner, a lot of those learnings are the same ones that you'd use to tell the difference between me smiling and me frowning. So you can take that network that was trained to do something else and make a relatively small modification of parts of it to do something new, and it'll work for the new thing. That's transfer learning. And it's because of that that we're actually able, on our Macs, to, within the time we have, and with devices whose GPUs are not well supported but by the training system we're using, to actually build models that are kind of leveraging all this work that was done training the original. So at this point, your Mac should be done. I don't hear any more fans whirring, so I think we're all past the training stage. Just to say one word about what we've actually been doing. So those black box shell scripts that we fired off are triggering Docker in order to run under Linux the TensorFlow machine learning library. TensorFlow is a library produced by Google. It recently released 1.0. It's very actively developed. It's industrial strength, state of the art. It's also well documented and well publicized and fairly approachable. One sort of conceptual point on TensorFlow, which we're going to get to later, is if you want to think about how TensorFlow organizes information and how you express a computation you want to do in TensorFlow, the right model is to think about something like Core Image or AV Foundation. So if any of you, who here has worked with Core Image? Can I have hands up, people who've done some Core Image? Or AV Foundation? Core Image or AV Foundation? Yeah, okay, so in both of those systems, you don't declaratively say, do this with an image right now. Instead, you work with an API where you define a set of operations that will get performed later. Like this will be a filter, this will be a filter. I want to express that this filter is hooked up to this one, is hooked up to this one, and that it starts with an image that comes in here. And only later, when you want to look at the results and try to pull an image out of the last point, does it all get computed. And because you're expressing everything in this standing back and wiring things together way, the framework can do a lot of clever work optimizing what's happening. It's the same way with TensorFlow. You are building up these objects that describe the connections of computation. Take this number, multiply it by 2, combine it with this. You can imagine this sort of graph of data flowing through it. And that's what TensorFlow is doing. So now, let's look at what we've done, and we'll see if our classifiers work. And after that, we'll dig in a little bit and see the network that we've built, see what it looks like. So it'll be sort of a tour of the parts of it.
Questions real quick?
Oh, yes, that's a good moment for that. Does anyone have any questions that they want to pose while I prepare this, before I dive into demo 2?
Hi. I was wondering on TensorFlow, is it like only for image classification, or can it be used for other?
Yeah, that's an excellent question. Thank you for that. It's a good one. No, so it's not only for image classification. It's not only for neural networks. In a sense, it's not only for machine learning. I mean, you can think of it, I mean, that's mainly what it's being used for now, and that's what's being promoted for. But you can think of it as a general framework for doing numerical computation. Like so for instance, like right now at my workplace, we have some computer vision models that use non-neural network techniques, use ensemble regression trees, use other sorts of systems. We have some things that are just a kind of pipeline for how you process images, if you're thinking of images as kinds of data. We're looking to migrate things into TensorFlow just as a general framework for doing this, because it presents a nice unified way to express any kind of computation in a structured way where you're organizing bits of it. So if you look inside what TensorFlow provides, they have a component of what they've released, which is I think called the toolkit, which is really more, something like regressions. You could do those in TensorFlow as well. Just like core image isn't just for cats, it's for any kind of generalized image processing. TensorFlow is for any kind of numerical computation that might be expressible as tensors, flowing through operations. Tensors, at the most basic level, like a number is a tensor. So 5 is a tensor. A vector is a tensor. A matrix is a tensor. Tensor is just the generalization of anything when you add another dimension to it. So it's a general purpose kind of numerical, deferred execution numerical computation framework. So let's just look right now at what came out of our. Any other questions?
Yeah, so we're running kind of short on time because of the technical issues this morning.
Okay.
We'd like to take a break, but we're going to skip the break and jump right into demo 2. If you do need to take a minute to go outside and use the restroom, just please do so quietly. And then I'm going to let Alexis go back to his demo.
Yeah, sure. So if anyone wants to take a moment to pop out, that's OK. I can reassure you, demo 2 is very relaxing. You're kind of looking through things your computer's done and exercising them in a simple way. And then there's some pretty stuff on the web page. No? OK. All right. Let's move onward. So if we just look here at what has come out of the training process, it took 5 minutes of time on my machine, maybe longer on yours or shorter on yours, depending on what else you were doing. And the last bit of the terminal output looks like this. You should hopefully see something like this. Let's look at these. And also, if we look at 2 new files that have been created, let's look at these first. So remember how I said how if you have a complicated model, it's not trained by just executing a formula. It's trained by multiple training steps. That's the meaning of the word step here. We went through 0 to 499, 500 training steps. And with each step, this script was producing more and more exactly tuned parameters for our classifier. Validation accuracy. So or train accuracy. Train accuracy here is up to 100%. So remember how I talked about there being sort of the set of all people and then the training set of people whose heights you're measuring? Well, we took about 600 images. But the script took only 10% of those images chosen at random and decided to use those as a training set. So this train accuracy equals 100% means that by the time the training process was done, the classifier was 100% accurate in being able to say, of one of those images, which category it fell into. But that's not really what we care about, because we don't want it just to be good for the training set. We want it to be used more generally. And this final test accuracy here at the bottom says that even though it tuned the network only by looking at that 10% of training data, if you now look in this case right now for the images that I took, it might not be the same for yours, depends on how varied you were really. The final test accuracy is 100%. So I should expect this classifier would always classify correctly for every one of the frames that I took. So in a certain sense, that's perfect. But in a bigger sense, what I want is something that's going to classify me in general, not just from those images. So we could ask, how much does it further generalize? It's this issue of overfit. Let me just look at a few more points here quickly. So if you look here in terms of files, just to take a brief tour, you'll see a text file, retrained labels. It's just, you can't read it here, but it's the words frowning and smiling. Those are the categories that we're classified into. And then we have this file, retrainedgraph.pb. It's about 90 megabytes. This is the new TensorFlow network that we've defined, which is different mainly in its kind of last layer. PB is for protocol buffer. It's a bunch of binary data that was produced by the training script. Now, let's classify an image. First, let's just look at the training data. So in tutorial package, I'm going to go step 4, and I'm going to classify image. And now I'm going to choose an image that might be in the training data, certainly in the test set data. I'm going to choose, say, you can all do this as well, the 101st image of me smiling. 100.jpg. Here we go. So we should expect this to be correct, given that I had 100% test accuracy. Takes a while to run. That's really just because it's loading the data, not because it's that slow to execute the network. And there we see a prediction. 94% chance that it's smiling, 5% chance that it's frowning. So that's good. So our model's working. Now let's try looking at the 101st image of me frowning. OK, 99% chance that I'm frowning for that image. Less than 1% chance that I'm smiling. So one thing you can see here is that the confidence of the prediction varies a little bit between these two cases. But what we really do is we look at the one that has the highest percentage and call that the answer. Now let's see how well it's really generalizing outside of our set. So let's classify a brand new image right now. So everybody, you've all got your working hard and listening faces on. I want to see the smiles coming out again. It's a great comfort to me. And let's launch Photo Booth again. And now I'm going to gather new data, just a still image. And we'll see if my classifier classifies it right. So square lozenge in the middle. There I am again. Hello, Alexis. And take an image of myself smiling. So everyone, could you raise your hand if you've taken an image of yourself smiling? Awesome. Great. So I'm going to put that on the desktop, just to have a place to put it. There it goes. And now I'm going to classify it using this same script as before by just taking that image and dragging it into the terminal. And what I hope to see is that it recognized I was smiling, even though it has never seen this data before, because that's a freshly gathered. Yes, so there we go. This successfully categorized that as a smile image, but you can also see that the percentage probability it gives to smile versus frown, well, oh wait, no, that's wrong. OK, interesting. All right, so this is an example of it not generalizing well. That'll happen too. So I don't know why it happened in this case, but that's interesting. So it could be that there was something about the way I was smiling in that last image that made it look more like the frowns to the classifier. I'm going to do another one, because that's interesting. I haven't seen that before.
Alexis,
Yeah.
if you like take some of your clothing off or do something or change the angle, it also affects the.
Yeah. Yeah, so this is the kind of issue of overfit that I want to get into later, but that's exactly right. So one question we can ask here is, have I built something that recognizes me smiling versus me frowning? Or have I built something that recognizes me smiling versus me frowning with this visual background, right? And with the lanyard in this direction? Have I built something that recognizes people smiling and people frowning in general, or just me smiling and me frowning? So I don't know what it was, but it could be, for instance, that when I was smiling, I always had my head in a particular part of the frame. And when I was frowning, maybe I was off center. And maybe all I've done is actually teach the classifier to know the difference between, being in this part of the frame versus that part of the frame. The way you would enhance your classifier so that it generalized better is smile in more different ways, like move around more when you're smiling, so that you're giving it a more generalized set of data. I'm going to try one just more. So has everyone here tried to do a classification on a freshly gathered image? Raise your hand if you have. All right, this will be an interesting test. So everyone, could you raise your hand if your classifier correctly classified the image? OK. Now put your hands down. Could everyone raise your hand if your classifier was incorrect in its classification of the image? OK. So I'm the only person who saw the hands. I'd say all your classifiers are perfect. No, no. I'd say that more of them were accurate than not. More of these classifications were accurate than not, but it's not by an enormous margin. Now, so far, I've just been giving you these shell scripts to work with because that lets us sort of get on with things right away. But in a sense, everything's a black box. Like, you're not getting to see how it all works in detail. And to some extent, that's inevitable given time constraints. But I'm just going to now go into a tool that lets you see the details of a neural network in more detail. We can use that to talk about how it works. Also, just to sort of see what's happening with these shell scripts, we could look at, say, the one we just ran. And you can see there's some gobbledygook here to make sure I'm running on the Mac. There's some gobbledygook here at the top to make sure I'm running in the right directory. Gobbledygook here. By gobbledygook, I mean the shell scripting language. To make sure that I've passed in an argument. This is reproducing the image resizing step that we did before. So I'm reproducing that kind of preprocessing with the SIPS command. But all of the action happens, all the science happens here in this call to Docker, where I'm basically saying run in the terminal. That big number is the image that we downloaded. So run from this little virtual machine in the directory called TF files that I've got right here on my Mac, putting it into this directory in the Linux machine. Run this little Python script. There's the command at the end to run Python called labelimage.py, and hand it that image that we just put in. So we're just going into a virtual machine and calling a Python script that's in there. I'm going to do. But before we go into that in more detail, let's have a quick look at the network. So now, please, in the console, run step 5, view in TensorBoard. OK. That seems to be working. Now I'm going to launch Safari. And put Safari here where you can see it. And now I'm going to browse to localhost 6006. And what I'm looking at now is a website that I'm serving from inside Docker. And let's talk a little bit about what this is. So first thing I want to highlight, is that legible? Not really. Let me make that better. Is that better? A bit. OK. Top-level scalars. So like I said, a scalar is just a fancy word for, could be just a number, could be a vector, could be a matrix, anything that has multiple dimensions and is a way of accessing numbers. Accuracy. So as we were training, for every step, we were keeping track of how accurate it was or wasn't. And this chart here, if I turn off validation. So I just unclicked validation, is showing the progress of training. So here you can see that training, really in this case, maybe for yours as well, accuracy went up quite quickly, and it was stable from 100 steps onward, and then it's making only smaller changes. That's the accuracy that's based on just comparing against the training data that was being used. If I look at the validation data, I expect to see something that's similar, but not very different. So you see the training validation accuracy is less than the training accuracy of what you expect. Now, if we had a situation where we had serious overfitting problems, then training accuracy would keep going up, because I'm just sort of memorizing the training data, but validation accuracy would start going down, because I've memorized the training data so well that it doesn't generalize outside of it. In this case, the script is using validation data, which is just another 10%. If you take a broader notion of validation and look at me just taking another image with a possibly different background, we saw already that like accuracy was, the accuracy was going down. Could you raise your hand if you've got TensorBoard running successfully? Okay, cool. There's another measure here, cross entropy. This is actually, I'm not going to explain this in detail, but this is actually the measure of error that's being used during the learning and training process. It's not looking at the accuracy itself for that. These are accuracy and training are both artifacts of the training process. If you look here in final training ops, I'm not going to explain this part in detail, but if you just, I want to point out two things. You have these path-like designations, which are used to reference variables within the TensorFlow memory system. And in particular, there's final training ops biases and final training ops weights. And biases has max, mean, min, standard deviation, and weights also has max, mean, min, standard deviation. So biases and weights are both sort of vectors of numbers where you can calculate univariate statistics. Those biases and weights, those aren't artifacts of training that you can use to see how training is going. Those are the actual values that are being produced by the training. Now let's go to the more dramatic part. If you go here to graphs, you can see the TensorFlow network itself. So remember that diagram we had going left to right? This is the same thing, but going top to bottom. Now, if you hold down Control and then, well, for me, it's double figure slide up and down on my Mac. You can zoom in and out. If you just tap and drag, then you can reposition. So I'm going to point out a couple features of this, and then we're going to go into a little bit on its details just to see what's going on. So a good thing to start is look right here in the very bottom. So data goes in at the bottom, and if we tap on this operation here, we get detail on it on the right, and you see it's called decode JPEG. So this is the operation that takes the JPEG file from the very beginning. This is the beginning of the pipeline. And if you look at this little bar here to the left of it, you can probably, I hope you can make it out on the monitor, it says question mark times 3. And what that means is it's describing the dimensions of the tensor that came in. Remember how I said how you take an image file and you just break it out into width times height times color channels? Well, there's 3 color channels, and what this representation is saying, when an image comes in, we don't know the width and height, but we know there's going to be 3 color channels. And if we look at what's happening further up, there's an operation called resize, where now afterwards it knows that we're looking at a 299 by 299 image. So that's one of the standardizations of the image that's happening in the course of execution. So I'm just trying to show inputs and outputs to give us a sense for how this fits together, and then we'll look a little bit at the guts of it just to sort of assess the complexity. So normally the TensorFlow network ends in this layer here called softmax. A softmax layer is a layer that turns some earlier representation that you have. In this case, that earlier representation is a single vector of length 2048. So it gets that, and then it turns that into the classification, where it says it's going to be one thing out of 1,000 different things. And it uses something called a softmax function internally to do it. But what we've done is we've added all this alternative route for the last layer. And it's because we were only doing operations here in the last layer that we were able to do it within 15 minutes of training time. The scalars that I was showing you before were final training operations. If you remember that path-like structure, they were things within final training operations. Now, if you click on the plus sign on any of these, you can see what's inside it. And you can start to see that it's actually quite a lot going on. That final training operation box wasn't itself a tensor, like basically a kind of number or vector or scalar, and it wasn't an operation, a thing that you do with a thing that you do with tensors to make more tensors. This box represented a group of those things together. It was a sort of subgraph of more operations. And in here are the actual weights and biases that we calculate in the course of training, and are then using when we exercise it. And these items here, accuracy, cross-entropy train, these are operations that aren't used in exercising the network. These are operations that are in the data flow graph just to do the training process itself. I realize that this is sort of a show and tell. Like, there's too much going on here to sort of say, like, here's how you'd rebuild TensorFlow from scratch. But I want to show you this tool because I think this makes it visual and makes it sort of accessible and makes really concrete the idea that this is really just a framework for expressing data flow. And I also want to give a sense of the complexity of the network. So if you look at this, you might say, okay, great, there's 48 operations that proceed in sequence. That's more than I want to manually manage, but it's comprehensible. But all of these, of course, also have internal structure. So if you go inside, you can see that these are convolution layers. There's a lot going on. I like just playing with this. So, how are we on time, Tammy, in terms of original starting time versus when we need to end to fit with other sessions? Okay. So I'm thinking if there's a bit of this demo I could skip to allow more time for the lab, but I think it's worth seeing a little bit of the. Let me do one more step in the demo part, and then I'll skip the rest, and that will allow time to explore this with the lab. So I'm trying to sort of open up the kind of black box that these shell scripts create a little bit to give you a sense of what's going on inside. So I've talked about TensorFlow being a deferred execution framework. We can interact with TensorFlow directly through a prompt just to get a sense for what that feels like. So let me go through that. If you can go back to the terminal and make sure you're in the tutorial package again and run the script optional login to container. Okay. So now notice that our prompt changed to root at gobbledygook, and we're in the directory TensorFlow. And that's because now we're inside the Linux machine that we've been accessing through these scripts. So instead of just going into Linux and making one command and getting the output, we're in a new prompt that's in there. If you look at we're in the directory off of the root called TensorFlow. This is actually the source code for TensorFlow itself. You can see in the directory TensorFlow examples, imagery training is the script that we used. There's comments here on Inception because that's a popular network. There's the code that drives TensorBoard, but since we're now in the prompt, we can just load up TensorFlow and work with it directly. Now, the best way to do that is through Python. So I assume everyone here is completely expert in Python. It's pretty straightforward. Python's really the best publicly supported API. So we're just going to go through a few steps just to do a really trivial computation in TensorFlow, just so you see what it looks like to build this stuff manually. So I'm at the Python prompt, import TensorFlow as TF. So that's just like an import statement in Swift. The as TF is just an alias so that I don't write TensorFlow, I just write TF. And I'm going to define a tensor, our first tensor, TF, and this tensor is just going to be a constant. TF.constant 42. So now if I look at what T1 is there, TF tensor, constant, so this is a string that you can use to reference it, or to describe it, shape, data type, int32. The shape here is just open and close parentheses because this, as a scalar that's just a number, it doesn't have more dimensions. If there were a vector, then shape would look different. I'm going to define another number, tf.constant 2. So now I have two tensors. One's called constant, the other's called constant underscore 1. It's giving these string keys that you can access them. Now let's say that I want to multiply two numbers. So I'm going to say the product. So I'm going to define a new object here, tf multiply t1.t2. Now I haven't actually done the multiplication yet because it's deferred execution. I'm just defining how these things will hook together. So if I look at product, I see product's also a tensor, but I haven't evaluated it. Now I need to create the infrastructure that will be used for evaluation. Just like if you're working with AV Foundation, you might create a capture session, which is coordinating all the different objects that you're putting together. Here we're creating a session object. And I'm going to run the multiplication. I'm going to evaluate it by calling run and putting the output there within the session. Oh, product. OK. So now I've got '84. So just to like recap, I have multiplied two numbers in Google's TensorFlow, in Linux, in Docker. This is the most cutting-edge way to multiply numbers in 2017. OK, I think this wraps up the demo point. So now we should go to the labs. Now I have a embarrassing confession to make, which is I think that the lab instructions you have are not as up to date as I'd like them to be, but I have a slide that describes what I think is the best thing to do in the lab. Now, I'll be honest, what I was originally hoping we could do in labs is we could take the models that we trained with Inception and then run them on iOS directly. The process of taking a TensorFlow model and porting it to iOS at this point in time in 2017, it would just be another black box script, but it would be a sort of much more deep and impossible to explain black box. So that's not the way I went with what I think we should be doing with the time right now in the lab. Let's go to the labs. What I think is most useful to do is to try to train another model that doesn't just use smiles and frowns, but is adding another category to it. So if you look at the way the scripts are laid out right now, they're very direct in that they all like directly reference smile, directly reference frown. If you go through the steps in the script and say add a third category, like not visually present in the scene, like if you take 10 seconds where you're not like right in front of the camera, you can see if you can build a classifier that will be able to distinguish that case as well. After the lab, I'll talk a little bit about what the process would be like for moving these models onto iOS. But at the moment, it's not particularly pretty. So I think it's better just to comment on it than to have a black box that does it. OK. All right. So that can close out of the console.
By the way, don't worry about not having time for the lab. We're going to treat labs like we treat. Oh yeah. So we don't have time for the lab exactly, But don't worry, we're going to treat labs like we treat optionals. Sometimes you'll have time, sometimes you won't. This time we won't, but we probably all agree that it was better to spend time watching Alexis do this than going off on our own. We all have the conference materials. We can do it on our own. It's not a big deal. We do have a lab. It's more like a meet and greet, so you can ask the instructors additional questions. He'll be there 10:45 to 12:15, I think. It's kind of right across the room at the Banneker, is the name of it. So if you guys want to just take a look at the changes that Alexis has and let him wrap up, then we'll move on.
OK. Does anyone have any questions here before I sort of summarize a bit? And I can also say a few words about the porting process if people are curious about how you'd move a model right now onto iOS. Any questions about what's come up so far? No? OK. Oh, yes.
Yeah, no, he's.
I often feel like, and hear other developers with more experience than me say about machine learning, that as cool as it is, it's way too advanced and we can't possibly learn it. Like mere mortals can't learn it. You have any thoughts to share on the accessibility of this? Do you have to be a university?
I think that's completely false. I think it's very accessible stuff. I think a good way to think about it is to think about the Swift language. So when Swift first came out, it introduced a lot of language features that were unfamiliar to people in Objective-C. And some of them were unfamiliar to mainstream languages, you know, like maybe like the protocol system, aspects of that. If you knew about like Haskell type classes, then you might say like, these are just like Haskell type classes. But like Haskell type class is Haskell was a sort of esoteric thing at the time. So when say Swift first came out, you might have some of the features in it you could have pointed to and said like, well, this is a difficult language because it uses esoteric features that only like language nerds like know about. But I think, you know, a couple of years later, everyone knows about these things because they're part of a mainstream language, and there's fantastic educational resources, not just at raywenderlich.com, but also at raywenderlich.com. There's fantastic educational resources that explain these things that used to be esoteric in very plain terms, and now that's just part of common knowledge. So it wasn't that these language features were like fundamentally, you know, unavailable to mere mortals. It was just that it was a niche thing that most people didn't know about, and now it's not because there's good resources for it. I'd say it's 100% the same with machine learning. Like there are parts of it that are mathematical. So if you wanted to, you know, be someone who's like inventing the Inception network, you know, for that there's a fair amount of like learning curve to figure out, you know, how you do it. That's a research project. But to make use of these things, to do something like we've all done right now, building a classifier on your system using a state-of-the-art network with data that you just gathered, it can be done because there's really good resources available for this thing now. It's not as good as the resources that are available for Swift, but they're coming out. And I think that Google's putting a lot of muscle into explaining this stuff in a clear way. So I think it's becoming one of these things where it used to be thought of as very hard, but really it was just very niche. And soon it's going to become very accessible. And it's going to be everywhere. It's going to be implicitly used in your APIs. I kind of wrap things up in shell scripts to make it easy. But you know, if you wrapped it up a little more, you could have a Mac command line app where you just like, you know, dumped in piles of images and then like pushed the train button and came back and you had a classifier. Like, you know, why couldn't you? Then you'd be doing machine learning, even if you weren't defining all the details of it. So I think it's going to become like that. Really, for me, putting this together, a lot of the work was finding disparate, somewhat well-documented, somewhat reliable pieces, and then packaging it in a way so that it could be delivered, so it's just like step 1, step 2, step 3. But I think that work's going to get done, and stuff's going to be very easy to get at. This actually touches on the thing that we don't have time to get into, which is porting to iOS. Porting to iOS right now is incredibly painful. Like, there is one piece of code, as near as I can tell, where someone has taken a complicated neural network and ported it to run efficiently on iOS, and that's Apple sample code. And you can use question there, Mark? There, do you? Yeah, the hardware is capable of doing it, but we're at a point where it's just early days technologically, so there's a lot of friction. So your options, like let's say you make an awesome model and you train it and it uses TensorFlow, and then you wanted to put it on iOS. You could host it on a server. That's boring, but it could work. Just like run it on Linux. You could actually embed TensorFlow in iOS, but it wouldn't run very performantly. But it could be done. Like they have instructions to support that. If you really wanted it to perform well, then you need to manually port it into one of two Apple frameworks, either Accelerate or, better choice, Metal Performance Shaders, because it's GPU accelerated. But what that would actually amount to is taking that whole giant thing that defined like 48 layers with lots of little details, and taking every single abstraction there and mapping it to a corresponding abstraction in Apple's API, and then taking all that data, that .pb file, and manually generating binary data that you read in iOS, and then put into the Metal Performance Shaders API. And it's been done. Apple's done it, and there's a script to automate it somewhat. But it's just a manual process. But I think this is going to be the kind of thing which is going to turn into something like MP3s. Like when MP3 was first invented, it was very awkward to use. Now it's just a file format. This will emit an MP3. This will read an MP3. You don't even need to know how it works. I think it's going to become that way for neural network models. Like there should just be export to .nn file format, and then Apple's framework should have a import from .nn, and then when things get standardized to that level, you will get GPU acceleration, and then it'll be easy to deploy. But the barriers to this right now are not fundamentally intellectual. They're just friction and stuff being a bit new. But it's a completely doable exercise. Like if you wanted to build a custom language, handwriting recognition thing right now, you could do it. You could do it. It's definitely doable. All right. So I think I'm getting the wrap-up slide, and I think these are the kind of wrap-up slides I wanted to offer, because I wanted to talk about the fact that, like I said, this stuff is becoming very accessible. It's interesting right now because of data, CPUs, money that's being put into it. And you shouldn't look at it as a frightening thing. There's a lot of good resources out there that make this very learnable if you think it would be a fun feature to add to your app. Even if you don't want to get into it right now, I think it's just going to come to the APIs near you very, very soon as a kind of delivered source. You don't need to be a mathematician. You don't need to be a giant corporation. You all right now built an image classifier based on a cutting edge, as of 2016, neural network model on your laptops. Within less than an hour. It's doable. As I discussed, these are options. The porting to iOS in particular is still a bit of a rough patch, but it's doable if you just sit down and power through some sort of tedious binary processing. If you want to learn more about machine learning, there's a lot of good public resources. I'm sure the RWDevCon video is in production or being dreamed up somewhere, but at the moment there's good stuff on Coursera. I highly recommend This Week in Machine Learning podcast. It's a nice way to just sort of ambiently get a sense of what people are doing. Google had a conference with videos and tutorial information they released recently. This guy, Siraj Raval, on YouTube, makes very accessible, fun, quick, watch this go kind of videos. If you want to get deeper into it, Deep Learning by Goodfellow, published just in 2016, is like a great resource. One way to think about it is, if you feel like you're behind on this stuff, you're not that far behind because it was invented a couple of years ago, right? It's not that hard to catch up. This is not like studying the history of Rome, where there's 500 years of deep scholarship on it. It's new, and it's like Swift 1.0. It's new enough that not that many people are really experts, I think, and it's very accessible if you want to dive into it, and it's fun stuff. If you have any questions for me, I'll be available for the kind of interactive question and answer later. You can always handle me on Twitter. I'm sorry we didn't get to port it to iOS, I really am. But I hope that this was interesting as a kind of grounding in basic concepts and a sort of walkthrough on your own machines of the current state of the art in technology. Thank you very much.